Erin Kara did her undergraduate degree at Columbia University, then went to University of Cambridge in England, where she did her master's and PhD. Now, when you go to Cambridge, you actually have only 3 years to do your PhD, but she basically was unbelievably productive, produced wonderful quality work, and was awarded a Hubble Fellowship. So the Hubble Fellowship is given by NASA, and just to give you a feeling, about 300 people apply, and they only get about 10. So we were very lucky to get Erin back to the US. So she came from Cambridge, where she's now at University of Maryland. She's an expert on black holes and very high energy phenomena. She communicates with satellites on space that make observations. She's going to tell us all about black holes, and in particular, a topic that is very dear to my heart, which is the digestion of stars by black holes. And even though it sounds like science fiction, this was something that was proposed almost a century ago, but only recently, about 10 years ago, we started having observational signatures that, in fact, black holes digest stars. Now, if you're not impressed by that, if you feed a grain of salt into a black hole, it will probably produce, the entire requirement for humanity, energy requirements for about, 10,000 years. And Erin is going to tell you now what happens when you digest a grain of salt, but in fact, a whole star. Thank you so much for being here. Let's, give a warm welcome to Erin. Thank you, Erin.
Okay. How's the mic? Can you all hear me? Yes. All right, great. Well, thank you, Enrico. Thank you, everyone, for coming tonight. It's such an honor to be here, representing also my peers at this conference on Tidal Disruption Events, and being in this beautiful city, in this beautiful space. So just a little overview about where we're going in this talk tonight. First, I'm going to give you an introduction about supermassive black holes that are 1 million or 1 billion times the mass of the sun. And then we'll talk specifically about tidal disruption events, where a star gets too close to one of these supermassive black holes and gets ripped apart. And I'll try to highlight some of the work of my colleagues in the room and give an introduction to this field. And then finally, as a last part, I'll give you an example of one particular tidal disruption event. And this is, I'll talk a little bit about my own work and how we are using these new techniques to probe closer to a tidal disruption event. But before I get into the science, the really nitty-gritty, I just wanted to make one correction to what you see in your programs. And it's really, there have been a lot of new results that we've been seeing this week. And this new result really is, the correction comes to my skiing abilities. So I think you may have noticed, if you read the bio, that it says that I'm an avid bunny slope skier. But that's no longer true, because Giuseppe Lodato and I, thank you, we conquered Buttermilk Mountain on Monday, and I went on a blue for the first time. Twice, in fact, twice. So I just wanted to make that breaking news, important result coming out of this conference. But really, in all seriousness, I wanted to start with this image from the Hubble Space Telescope. This is the Hubble Deep Field, and it is my favorite astronomical image. And I love it because it just shows the vastness of the universe. All of these splotches that you see here are galaxies. And some of those galaxies are nearby, and by nearby, I mean like millions of light years away. And some of them are very far away from the very early universe. And it's just showing in one image all of those galaxies together. And the other reason that I like to show this image is because the story of it is really cool as well. So in 1995, the Hubble Space Telescope had just launched. In fact, there was an issue, and astronauts had to come and fix the telescope. But in 1995, it was working perfectly, and we were getting these beautiful images that I'm sure that you can all envision. And the director of the Hubble Space Telescope at the time, Bob Williams, he said, well, let's take this telescope that everybody's excited to use and point it to nothing. And he said, let's look at a point in the sky that is 1/30th the size of the moon on the sky. So if you put your thumb up like this to the sky, the angular size of the moon is about the size of your thumb, so 1/30th of that size. That's about 1/millionth the size of the entire sky. And they pointed the Hubble Space Telescope for 10 days, consecutive days, and this was the image that they came up with. So out of nothing came all of this. And in addition to it just being a remarkable image that really puts astronomy in context, we've gotten a lot of science out of it as well. So some of those galaxies are elliptical galaxies, like this one. This is ESO 325 minus G004. We astronomers, we're really creative people, so we come up with these nice names. And you can see this elliptical galaxies are really just like blobs of stars. They're kind of like these three-dimensional blobs of stars, and we think that they are formed by galaxies merging together into this into a larger galaxy. And some of the galaxies that you see in the Hubble Deep Field are these beautiful spiral galaxies, and these are kind of the ones that we're all more familiar with, the more beautiful ones. If anyone has had a Mac in the past 10 years, this is the default, desktop figures that you've seen. And this is the Andromeda Galaxy, and it's just another beautiful Hubble Space Telescope image, and it's 2.5 million light years away. And one reason that I love this picture, that it holds a dear place in my heart, is a little story that I have. So about a year ago, I was invited to go back to my elementary school and give a talk to the kindergartners about what it's like to be an astronomer. And I had prepared a bunch of slides, just basically beautiful pictures from space. They're kindergartners. And I showed them this beautiful image of the Andromeda Galaxy. And I told them this one kind of fun fact, that the Andromeda Galaxy, it's our nearest galaxy to our Milky Way galaxy, and it's the only galaxy that's coming towards us. And in 4.5 billion years, the Milky Way galaxy and Andromeda are going to merge and maybe form an elliptical galaxy like you saw on the last slide. And that was supposed to be it. It was just, one kind of slide, and we were going to move on and talk about planets and whatever. But 1 million hands went up in the air. These kindergartners freaked out because they were just so worried, like, what's going to happen to us when the galaxy merges with our galaxy? Are we going to feel it on Earth? And it just completely derailed the conversation. And I said, oh no, we're not going to feel it on Earth, because by that time the sun will have become a red giant and will have engulfed our Earth in flames. And that's basically the last slide that I showed. It was just completely, Anyway, so that's the Andromeda Galaxy. And going back to this Hubble Deep Field image, the thing that really is amazing to me is that all of these galaxies that you see, or nearly all, if not all, host a supermassive black hole at their center, from 10 to the 5, 100,000 to 10 billion times the mass of the sun. And these galaxies, or these black holes, they're present in all galaxies. We can probe these black holes around these galaxies, inside these galaxies. So if we look, the best evidence that we have of a supermassive black hole at the center of a galaxy is in our very own Milky Way galaxy. This is Sagittarius A star. It's in the constellation Sagittarius, and that's how it gets its name. And it's about 4 million times the mass of the sun. And the reason that we know that it's there is because we can see the influence that it has on the stars around it. So this is, I'm going to show a movie here. This is really a heroic work done by the UCLA group using the Keck telescope. And you can see at the center of this image where the star is, That's the location of Sagittarius A Star, this 4 million solar mass black hole. And all of those bright points that you see are stars. And so they've been tracking the trajectory of these stars for about 40 years. So this is starting in 1995, and you can see here, the movie will start. So here a star comes in, and it gets whipped around, and they're orbiting around this thing that's not producing light. And because we know the mass of the stars and we can track the orbits of these stars, we can infer that the mass of this black hole must be around 4 million times the mass of the sun. So Sagittarius A Star is a special example because it's the nearest supermassive black hole to us. It's about 25,000 light years away. And so we can actually see these individual stars. Now, in every other galaxy, we can't trace these individual stars, but we know from the bulk motions of stars, we infer that there must be a supermassive black hole at the centers of nearly all, if not all, galaxies. So that's our nearest supermassive black hole. And just recently, Nature published in Nature, December 2017, so just about a month ago, they found the furthest supermassive black hole. And this is an 800 million solar mass black hole in a significantly neutral universe at a redshift of 7.5. Redshift is how astronomers measure distance, and 7.5 is really far. And if you prefer the translation from Science Daily magazine, monster black hole discovered at cosmic dawn. So we're able to probe these very supermassive black holes even when the universe was just 690 million years old. So even when the universe was just 5% of its current age. So all of those black holes that we see out in the universe, about 10% of those are ones like this one, and they're called active galactic nuclei. And they have lots of material falling into those black holes. And that material circularizes and produces an enormous amount of energy. And I'll go a little bit more into detail, but this is 3C273. 3C is the third Cambridge catalog. I got to get my Cambridge University pride going. So this is just number 273, and it was the first active galactic nucleus that was discovered. And I love this image because within the same frame, you see at the center, that's this supermassive black hole with a lot of material falling into it. And it's almost 1 billion light years away. But in the same frame, you see a star up in the top left-hand corner. And that star is about 1 million times closer. It's a foreground star. But this black hole, this accreting black hole, is much brighter in the image. And so if it's 1 million times further away from that star, and the flux of the brightness of this thing goes as the inverse of the distance squared, that means that this accreting black hole is 1 million times more luminous than this foreground star. That's a lot of power coming out from this, produced from material falling into this black hole. The other thing that I want to point out is that this image, you can see the crosshair structure in the center there. That's an artifact. That's due to the support structure on the Hubble Space Telescope. And it's just an artifact there. And when Hubble sees a point source, something that they can't resolve spatially, you get these crosshair structures. And so you see, that's saying that and as well, the star in the top left-hand corner also has these crosshairs. So it's saying that this emission coming from around this black hole is very compact, and we can't resolve it with our telescopes. If we could resolve it, if we could zoom in to that innermost region around this supermassive black hole, this is maybe what we would see. So this is at the center there's your black hole, and there's all this material, this hot gas that's orbiting around this black hole. So it's kind of a popular misconception, and I get asked this question all the time about why don't things just get sucked into black holes? Don't they just suck up everything around them? And that's not exactly true because, well, if you think about, let's say I have a black hole here, and I have a point, like just an atom of gas that I want to aim it directly at this black hole. Unless I have impossibly good aim, it's not going to directly end up, this point particle of gas is not going to directly end up in this black hole. In reality, it's probably going to get close and then whip around and eventually start orbiting. There's lots of gas that is eventually going to orbit and settle into this disk that we see. And as the material eventually falls closer and closer to the black hole, it's moving very quickly. There's a lot of friction between the gas. And this friction causes this accretion disk, we call it, to get very hot, so hot that it radiates light. And this is a lot of the light that we see, that you saw in that image on the last slide. And in this kind of regime that we're in, to a point, basically the more material that you accrete onto this black hole, the more radiation you'll get out. But there is a limit to this process. This is the Eddington limit. This is the theoretical limit for how fast you can grow a black hole. And maybe it's a little bit technical, but I wanted to describe it to you guys because it's something that we have been talking a lot about in this conference and is important for understanding tidal disruption events. So this Eddington limit is the case of, let's say you have a spherical ball of gas and it's accreting onto a black hole. At some point, the radiation that's produced, this radiation will have a force outwards, and at some point, the gravitational force inwards of this gas is going to be balanced by the radiation force outward, and it'll be balanced. And this is the theoretical limit for how fast you can grow a black hole. So now we can go back to this brand new observation that was just published a few weeks ago, and we can say, okay, wow, this is actually, it's even more remarkable than just finding one of the earliest black holes. Basically, if we know that if a black hole must be formed from, in a normal way, which happens from a supernova explosion, and the material collapses into a black hole, producing a black hole that's maybe 10 times the mass of the sun, in order to grow that black hole from the very beginnings of the universe to 690 million years later, when we observe this black hole, you're going to have to accrete at rates above the Eddington limit. So this is a big fundamental question in astrophysics, is how do you grow these supermassive black holes? Maybe you need super Eddington accretion. Maybe you need to exceed this theoretical limit, or maybe you need to just start out with a bigger black hole at the beginning. So that's one of the main motivations for studying what were tidal disruption events. We want to understand, can we break this theoretical limit? And this is where tidal disruption events come into play. Tidal disruption events are, one star's death gives life to a black hole. That's the title. When a star gets too close to a black hole and falls into the black hole. And there are predictions that this event may cause super Eddington accretion, and that's why we care about studying them. So I feel, just to tell you a little bit about black holes, I think our logo really says it all. This is a star, a maniacal-looking star, skiing in Aspen, and it gets too close to a supermassive black hole and it falls in. But in reality, the details are a little trickier than that. These are two canonical pictures that we've seen many times in people's slides this week, and I feel obliged to also show them to you. So this is from Martin Rees's 1988 paper, one of the earliest papers talking about theorizing about when a star gets too close to a supermassive black hole. And you can see, where's my pointer? That here's your star, here's your supermassive black hole at the center there. This star comes in, and at some point, which we call the tidal disruption radius, the strong gravitational forces of this supermassive black hole are stronger than the self-gravity holding this star together, and it gets ripped apart, and it causes this, this debris to spew out. And you can see some of that stellar debris will just continue on its original trajectory, but some of that material, that stellar debris, is bound, gravitationally bound to the black hole, and will fall back towards the black hole. And on the right here, I'm showing this is the fallback rate, how fast that material, that stellar debris, can fall back towards the black hole as a function of time. And this is a very characteristic result from a tidal disruption event, that you have a lot of material is starting to fall back, and there's a lot of fall back towards the black hole, and then it decays over time as this functional form t to the minus 5/3 power. And so what's interesting, though, is that this fallback rate onto the black hole can be 100 times more than the Eddington limit, this theoretical limit for how fast you can grow a black hole. So that's what made people really excited about the potential for measuring, for observing these things in the universe. And what's amazing is that we actually do see these things, and that's really why we're all here for this conference, is because we do see these things in nature. So this is one of the best examples of a tidal disruption event by Suvi Ghazari, who's one of the organizers of this conference and has been a real pioneer in this field. And what you're seeing on the y-axis here is, this is just the brightness of the event as a function of time. And this is the points in different energy bands. And you can see, basically, this is a quiescent galaxy. It wasn't one of these active galactic nuclei with a lot of accretion onto the black hole before. Before, there was not a lot of material falling into the black hole. But all of a sudden, you see this brightening, and then on timescales of a year, this decay as t to the minus 5/3. And this was really a telltale sign that you are seeing a tidal disruption event. And so now, once we think that these events are actually quite common. Once every 10,000 years in a galaxy, in one galaxy, a star will get too close to a supermassive black hole and get ripped apart in one of these tidal disruption events. And this is predicted by a theory. This is work by Nick Stone, who's one of the participants of our conference. And this is really matched by what we're observing as well. This is the cumulative number of tidal disruption events and the year that they're discovered. And basically, since 1995, we've been increasing our number. Now we have 24 of these tidal disruption events that we've observed. We see about 2 of these a year. And we're really, right now, at a very exciting time, because all of these surveys, they're basically looking, even though this tidal disruption event happens once every 10,000 years, we're able to monitor with these large optical surveys, we're able to monitor tens of thousands, hundreds of thousands of galaxies a year. And so we actually end up seeing these things quite frequently. But in the next, well, actually right now, this facility called the Zwicky Transient Facility and other optical surveys, the Aspen survey being one of them, they are really improving their sensitivity, and we should expect that we're going to be able to probe more galaxies, and we should see about 30 tidal disruption events a year. And even just in a few more years, another huge breakthrough with LSST, another optical survey, we should see 1,000 of these a year. So we're really at the brink of something exciting, and that's, I think, why we're all here, is that we are so excited for the future, and we have to get prepared for these large numbers of tidal disruption events that we're going to see. So just a little bit about some of the questions that we've been mulling over this week at our conference. You know, I told you that this fallback towards the black hole can be 100 times this theoretical limit for accretion onto a black hole. But you also remember that I said that material will get into, it just doesn't get sucked into a black hole, that material will orbit around this black hole, and it's quite happy to orbit around the black hole. So even though you have fallback towards the black hole that is at an incredibly high rate, how do you actually get that material to fall into the black hole? And that's a big question in our field. And can this rate of accretion onto the black hole exceed this Eddington limit? And then finally, what does it look like when a black hole exceeds this Eddington limit, if it does? So this question about can material actually accrete onto the black hole very quickly has been studied by a lot of people, as I said. And I'm going to show you some hydrodynamic simulations by Clément Bonnereau, who's another participant here. And what you're going to see is this is the debris from this after the tidal disruption event has happened. You have this debris some of it is falling back towards the black hole. And you can see the white dot there is the black hole. So we can watch this happening. And in this inefficient circularization, we call it, you know, the stellar debris is mostly happy to just orbit around the black hole, and eventually these streams will collide with each other, and eventually the material will slowly fall into the black hole. But the question is, like, I mean, this is happening this is a slower process, and then maybe the rate of accretion onto the black hole isn't at these super Eddington rates. The other possibility is that you have efficient circularization, where the material intersects with the stellar debris and can circularize much more quickly. And I should say that a lot of people have been working on this, and there's lots of debate as to which of these two scenarios is happening, or if they're both happening, and where the emission is coming from in both of these scenarios. So this is one of the big questions that we're mulling over. I was thinking about this when I was on Buttermilk Mountain on Monday, and I was thinking, actually, there's maybe a good parallel to the skiing that maybe you guys will appreciate. So let's take the case of me and Giuseppe. He's a great skier. You're a great skier. And, you know, we were having a great day. We did the 2 blues, right? And, you know, we decided at the end of the day, like, okay, we'll come down one more time, and then we'll stop and we'll, you know, go back to the lodge. And so Giuseppe goes down. He's a very efficient circularizer. He comes down and he stops on a dime. He does that, you know, hockey stop. He whips around and he stops, and he can go into the lodge sooner than I can, because this is me. I'm coming down. I'm going at a good clip, right? I was okay. And I'm coming down, and eventually, you know, I have to stop somehow. And I'm doing the pizza wedge. I'm doing some wide angle turn, and maybe I'll hit some other skiers. I'll stop eventually, but it'll take me a lot longer to get into the lodge. And so that's kind of what we think is happening. I'll show you now these simulations again. So Giuseppe on the left here has done this hockey stop. And basically the differences between these two simulations is that the stellar debris has gotten is on a trajectory that's closer to the black hole originally. And because it's close to the black hole, it gets whipped around faster, and it circularizes a lot faster. And it can accrete onto this black hole a lot faster than in, this pizza wedge kind of inefficient circularization scenario. So if you think that this efficient circularization process can happen, then you can accrete material onto the black hole at rates that are higher than this theoretical Eddington limit. So let's think about that a little bit more. Is this Eddington limit really a limit at all? I told you that the Eddington limit is for this spherical ball of gas, but maybe you can get around this limit by just breaking the symmetry of this system. So if you have, on the right here, this is one way that you could break this symmetry, that you have material flowing in an accretion disk, in this puffy accretion flow, and then you have radiation coming out in the polar direction. And that's one way that you can avoid this Eddington limit. So that's really one of the questions that we want to ask is, do we see this super Eddington geometry in these tidal disruption events? And so that brings me to the last part of my talk, showing you an example of, from my own work, of a tidal disruption event that really does seem to be super Eddington. So this is Swift J1644, another one of these great astronomy names. It was discovered by the Swift telescope. And this was, again, one of these, it was just a normal galaxy with a black hole at its center that wasn't accreting a lot of material. But then on March 28th, 2011, the Swift telescope saw a huge amount of light coming from this galaxy that previously had shown no light. And you can see, this is now the brightness again as a function of time. It decayed over time as this t to the minus 5/3. It really looked like it was one of the most luminous tidal disruption events that we'd ever seen. And just energetically, it seems that this must be one of these super Eddington accretors, where you have material flowing in, but you have incredible amounts of luminosity that are escaping. And so we wanted to really probe, what does it look like? What does it really look like? What does this accretion flow look like? But again, that's hard, because we can't resolve these things with our telescopes. So this is what this tidal disruption event, Swift J1644, looked like in the Swift XRT telescope. And again, that's it at the center. And you see these, again, these are just instrumental artifacts. It was seen as just a point source, and we couldn't resolve the actual accretion flow structure. But we still want to know, what does it look like when a black hole exceeds the Eddington limit? So that brings me to a technique that I've been working a lot with that helps us see these accretion flows without actually being able to image them. And it's using a technique called reverberation mapping. I think it's something that in some ways is very intuitive to us all. We hear echoes. I'm speaking to you now. This is a schematic of what's happening. I'm this bullhorn here, and you're sitting in this large room. This is you listening to me. You hear some of what I'm saying directly, but you can also hear the echoes off of the wall. And this is just a way to say that graphically. Here's this direct sound from me, and you hear echoes. There are not just one echo, but there's multiple echoes, and sometimes it takes longer time. But if you were if you were able to measure all of these echoes that you're hearing, you'd be able to map out what this entire room looks like without actually being able to see it. And we know that if we take this time delay that we're measuring between these echoes, we know that sound is moving at the speed of sound. And so we know the distance between me and the walls. We can map out this room. So the details in tidal disruption events are a little bit different. Instead of sound echoes, we're talking about light echoes. And it's not so easy that it's just a reflection, like a mirror, off of the accretion flow. Really what happens is that, we see some flash of light, and then we see an echo off of the accretion flow. So we see some flash of light here, and we want to measure this echo off of this accretion flow. And it's not like a mirror, as I said. The real process is, you may have to remember back from your chemistry days in high school, a photon comes in, hits this accretion flow, and there's lots of atoms in this. This is made up of a collection of atoms. A photon, a light particle, comes in and hits one of these atoms, and it excites an electron up to a higher energy level. And as that electron decays back down to its energy level, it will release a photon at a specific energy level, the difference between these two energy levels. And for the case of iron, that's what I'm going to be telling you about, the case of the iron atom, this transition is at 6.4 kiloelectron volts, a very particular energy. So that's the kind of echo that we're trying to measure. We're trying to measure the time delay between like this direct sound, or this direct light that we see, and this iron K fluorescence at 6.4 keV. The other reason that it gets a little more complicated is that it's not that we see just a flash of light, just like how it's not that I'm giving you an isolated pulse and then you can listen for the echoes. I'm constantly talking to you, and so it's a little bit harder to pick out exactly when these delays are happening. This is the same thing that's happening in the light coming from this tidal disruption event. It's not just one pulse of light. This thing is constantly re-brightening and getting dimmer and dimmer and over as a function of time. But what we were able to find, and this is like one of these magical scientist moments where you find something in the data and you just get totally, you're so excited. It's why you become a scientist, I think. We found these reverberation light echoes in a tidal disruption event. And this is just showing you here, this is, again, the brightness as a function of time. And now I'm showing you this primary source flickering. And this is the light curve for this iron K fluorescence line, this reflection off of the walls of this funnel. And you can see, even by eye, that there's a slight delay of the line with respect to this primary flashing source. Another way of saying that, this is really how I produce these, how I study these things, really the data that I'm most interested in is a projection like this, where you see this iron K line is lagging behind this primary flickering by 100 seconds. And so we can take this in a kind of simplistic way. It's a little bit more complicated in the end, but in a simplistic way, we can take this time delay that we see between this primary flash and the reprocessed emission off of the accretion flow. The time delay times the speed of light will give us a distance. And that turns out to be 30 million kilometers, which doesn't sound like a very small distance. It's about the size of our solar system. But when you compare that to the size of this galaxy, we're actually able to measure incredibly small scales around black holes that are very far away. So this was really exciting that we were able to see these light travel time delays, these echoes. And we can put together, we got excited, we wrote a paper, we talked to the NASA press people, and this is kind of showing you, putting together what we think is happening. So there at the center is a supermassive black hole, and a star comes in. This is an artist's representation. A star comes in, this stellar debris circularizes very fast, and forms this accretion flow structure that's incredibly luminous. And what we think is happening with these light echoes is that you're seeing some pulses of emission, continuous pulses of emission, and you're mapping out this time delay due to this reprocessed emission off of the disk. So that's really all I wanted to tell you about tidal disruption events and how we look at them. So I hope I convinced you that black holes are cool. They sit at the centers of all galaxies. And when a star gets ripped apart by a supermassive black hole in a tidal disruption event, it offers us a unique way of looking at how this accretion process happens. And lastly, we were able to measure these light echoes that was allowing us to basically see what an accretion flow looks like around a newly formed accretion disk around a black hole. So, thank you.
Thank you so much for a wonderful talk. We are going to take questions for about 15 minutes, and I'll try to pass around the microphone.
Two questions, if I may. You didn't talk about dark matter as it relates. So the first question in forming supermassive black holes, is there any evidence of direct collapse of dark matter and dark matter stars being a source of the very early supermassive black hole that you described? That's question one. And question two, when you talked about the matter accreting in and the Eddington limit, that also appeared to me to assume regular matter. And what can dark matter easily exceed, since the outward radiation pressure, I believe, would have no effect?
Yeah, that's exactly right. So that's right, I didn't talk about dark matter, mostly because it's not very important for these kinds of scales that I'm showing you, very close to these black holes. So these galaxies sit in these dark matter halos that are actually, most of the mass. And yes, some of the dark matter could fall into a black hole as well. But you'll remember what I said, that if you were taking a dark matter particle and you were trying to aim it at a black hole, it's a very hard thing to do. And it doesn't have it's easier for gas to do that, because gas will eventually form this disk and will eventually, because it interacts with other particles of gas, it will eventually form this disk, and then that material will fall into the black hole, and really that's how this black hole can grow. So yes, in principle, dark matter can also grow a black hole, but it's just in practice, because it doesn't interact with anything, that's not the effect that's most important. And then what your other question was about the Eddington limit, and what would happen if dark matter was falling into a black hole. Well, then in that case, because the light wouldn't be able to push on anything, it wouldn't interact with this dark matter, and so it would just be direct collapse into the black hole. So yeah, it can easily exceed this Eddington limit, but again, actually for it to directly fall into a black hole is a very challenging thing, because it's not interacting with anything else. But that's a great question.
My question is, you showed early on that you could determine the size of the black hole by the motion of the stars around it, and those stars have mass. I understand you can determine the distance of the stars by the redshift, but how do you determine the mass of those stars?
So the mass of those stars is pretty well understood. We know the temperature of these stars. We can measure that very accurately, and then we know how much mass you need to produce the luminosity and the temperatures that we see. So that's been done we've known that for a very long time. And it was really just being able to map out these orbits that gave you information about what the other massive object was. Yeah.
Yeah. You talked about the iron being the thing that you were looking at for your electrons dropping back, and you were looking for your 6.4 keV. Doesn't that sort of assume what the target star's composition was? And if the target star's composition wasn't like that, then wouldn't you have seen something very, very different?
Yeah, no, that's an excellent question. And it's actually something that we thought, basically all you need is a little bit of this iron to be able to see the emission that we're seeing. But originally, we thought just like you, that maybe because we're seeing iron, we could rule out different kinds of stars that it could be, that it couldn't be like a white dwarf star. But it turns out that all you need really is just a little bit of that iron to be able to see the reprocessing. But you're thinking totally in the right direction, yeah.
Yeah. Quick update on that one. If that's true, if you only have a small amount of iron, does that then mess up your amount of energy that you think is actually being thrown off by this thing, depending on the actual iron concentration of the star that's being consumed?
Another really good question. So yeah, I mean, if there is, this is kind of getting into the complexities of this, but if there is much more iron than you might expect to see this, in addition to seeing it in the lags, you'd also see it just a very deep, big spectral feature. And that could kind of skew how you interpret these time delays that we're seeing. Yeah, it's a good question, and I have a better answer for you, but maybe it's getting a little bit into the nitty-gritty of it. Yeah.
Yes, go ahead. Just speak loud.
When our galaxy and the Andromeda Galaxy come together, two central black holes will start to advance and will inevitably come together.
Yeah.
It must be happening out there in other situations as well. What happens with those 2 point masses between the accretion?
Yeah, That's a really great question. So I only talked about growing black holes through this accretion process where material slowly accretes over time and grows the black hole bigger and bigger in mass over time, slowly. But then another very obvious way to grow black holes, and is a very important way of growing black holes, is that these supermassive black holes will be attracted to each other. They'll probably whip around each other a couple of times. There have been a lot of simulations of this, and eventually merge into one larger black hole. And that's similar to what you've probably heard about the big gravitational wave detection from, I guess 2 years ago now, from LIGO, where it wasn't supermassive black holes, but we called them intermediate mass black holes, where two 30 solar mass black holes merged together. They did this little dance, and as they got closer and closer, they produced these ripples that LIGO detected, and then we finally watched them merge. So yeah, we think that it's happening. We've never directly seen two supermassive black holes merging. The timescales for that to come together are going to be a lot longer. But there's another instrument. What they want to do is put LIGO, this ground-based interferometer, they want to put it up into space and make a much, much bigger interferometer that would be able to probe these supermassive black holes merging into each other that we theoretically think must be happening, but we haven't been able to observe directly.
I'm going to take some questions from our young audience.
Hi. So you said that the like the supermassive black hole that we kind of know about right now is in the center of our galaxy.
Mm-hmm.
So is there any possibility that all the mass from our galaxy kind of going towards the center is one of the reasons that helps form that black hole in the center of our galaxy?
That's a really good question. So definitely there is this black hole sitting in this large galaxy. This black hole is about 1,000 times less massive than the galaxy. But all it takes is some of the material from this galaxy to be able to accrete onto the black hole. And the question really is, the kind of hard part is, how do you get material that is happily orbiting, like how we are happily orbiting around our sun? We're not just plunging into the sun. How do you actually get that material to lose the angular momentum that it has in order to fall into the black hole? And that may be done by galaxies merging together, for instance, or like little things, little smaller galaxies kind of getting close to our galaxy, and it kind of disrupts things and it messes up this clean orbit and then finally allows material to fall into this black hole. But yeah, that's how we think these things will grow. And what's interesting is that the galaxy and the black hole are evolving together.
You can speak loudly.
Does the matter actually have to enter into the singularity to grow the black hole, to grow the event horizon?
That's a good question. The question was, if you didn't hear it, does matter have to actually enter the singularity in order to grow the black hole? And so, I mean, that is an inevitability that the matter will. So once it passes this event horizon, which is basically the last time we have information about it, it will plunge just ballistically into this, into the black hole. So or once it really passes the inner edge of this accretion disk, that's a more accurate way of saying it, then it will just fall into this black hole. So, yeah.
So sorry, just to clarify, so once you get inside the event horizon, you can just beeline it for the singularity?
I mean,
Orbiting?
I think it's a pretty ballistic process. But then again, I don't think we have no information about what happens within the event horizon. So it's not a question that I, as an observational astronomer, can answer. Yeah.
Is there any evidence or any thought given that the black holes may have existed before the Big Bang?
Well, what happened before the Big Bang? I mean, yeah, I mean, I guess in these multiverses, if that's the scenario that you want to go with, then those black holes could well exist in those as well. Yeah, so I don't really have a much better answer than that because we don't have any information. We only have this one universe. I'm sorry.
Do you need a microphone or you're?
Oh, that'll be good. Do you see any, contribution for, like, say, synchrotron radiation from the accretion disk adding to the friction in the accretion disk?
Yep.
That might be being released, and that could be another escape valve for energy leaving.
Yeah.
Material that would allow it to fall in something faster.
Yeah, so this is a pretty technical question. And the short answer is that yes, there's also a lot of synchrotron. I didn't even talk about that, but that was a big part of the discovery, that there's a lot of synchrotron emission. In addition to the accretion disk getting so hot that it radiates thermal emission, it also, there's strong magnetic fields, synchrotron radiation is also involved. And that is a way that a lot of the emission is able to escape. a lot of the energy.
A lot of gamma rays leaving that situation also, especially at the very beginning where it gets super, super close?
So there, in this particular observation, this is another technical question, there were no gamma rays detected, only up to hard X-rays, high energy X-rays, but there was radio emission, strong radio emission that was detected, which was a clear signature of synchrotron radiation. Yeah.
Yes.
In the process you showed us, is it possible that the nuclear structures are changing as they're coming into the black hole? Like you said, it's iron. But is it possible that the force is great enough to change hydrogen to iron as it comes in the same way that it's formed in?
Yeah. Well, oh, okay. So the question was that as this stellar debris comes in, we know that there's, the star has a lot of hydrogen in it, but maybe it's getting compressed by these, the tidal forces of the black hole, and maybe this compression can actually, make the hydrogen convert into helium. And I think some other people in the audience are working on this problem, especially for when a white dwarf gets tidally disrupted by an intermediate mass black hole. That process could ignite fusion. Yeah. So I don't think that there's any evidence that we're seeing that. It's a very hard thing to observe because you're only seeing because we haven't seen signatures of it. But yeah, it's a good idea.
Maybe if
you're working on it. So.
No, I was just going to make the analogy, which I thought it's interesting. For example, the way that we search for lead painting in the walls. We take an X-ray gun, we irradiate the wall, and then we see the reverberation, the fluorescence light, of lead in the spectrum. And even though there are very, very few atoms, we actually can identify that there's lead in the painting without actually having to take out the lead. So you just only need a very few atoms to actually see. So I guess if we continue your analogy of sound, but also X-rays in the wall, X-rays in the wall also give you fluorescence, and that's actually how we can detect lead painting from the wall.
Yeah, good analogy.
We have time for maybe a couple more questions. Yes.
Your accretion disk, you sort of portrayed it as this very, very thin thing. I'm wondering how the thickness of this accretion disk enters into all your calculations.
Excellent question. And it's something that we're thinking a lot about as well. And a lot of people in this room are doing simulations of these super Eddington accretion flows to answer that very question. So as this material accretes onto this black hole, this disk is, as I said, it's getting very hot, and it produces a lot of light. Those photons produce a radiation force that will puff up this accretion disk. And so you won't have this thin disk structure that I showed in the case of just normally active galactic nuclei, things that are accreting at rates that are lower than this Eddington limit. But once you get to this high Eddington regime where you have a lot of luminosity, then radiation force is important and will puff up your disk. And so what I've shown you here, and again we can talk about the details of it, was that we were seeing actually the effect of, this radiation force that's puffing up the disk, but also pushing material out and causes these fast winds to be blown off of this accretion flow. And so the thing that we were measuring, in addition to these light travel time delays, these reverberation echoes, is that we were able to see that this material was also outflowing. Yeah. And you see that as because of a blue shift of the iron line, in case that is a meaningful terminology.
Hi. So I know that in a black hole it's black because no light can get past it, but does this light just go directly into the black hole, or does it also circle around it before it enters.
That's an excellent point, that we're not seeing any emission from coming within the event horizon. No light is escaping. That's really, the definition, by definition, of the black hole. But the gas that's orbiting closest to the black hole is producing a lot of radiation. And those photons that escape, some of those photons come to us directly, but some of those will be so close to the strong gravity of this black hole that those photons will also start orbiting. And some of them will be bent, and then we'll see them after they've bent over the black hole, and some of them will just keep orbiting. Yeah, that's an excellent question.
Okay, last question. Yes.
Does space-time get sucked into the black hole? And if so, how does that impact the accretion? And does that in any way give us some insight into what might be happening inside the event horizon?
So the question is, does space-time also get sucked into the black hole? And the answer is that space-time is is curving due to the black hole. Space-time is being affected by this black hole, and as it grows, as material falls into it, the space-time will get more and more curved because the black hole is more and more massive. But it's not that space-time itself will fall. Yeah, the black hole affects the space-time.
Okay, on that note, let's thank Erin again for a wonderful talk.
Thank you.